this video, we'll be looking at the tangent function, which is 6j in our textbooks. Okay, so from a previous video, you would have looked at the basic graph of y equals tan x. As you can see, it has a period of pi as you go from left to right. It has a whole bunch of x-intercepts as well. It goes to the origin. And you would have seen all the various asymptotes, the equations of which you would have learned how to derive. We also looked at a more complicated example of a tan graph, and there's a whole bunch of working that went behind it as well. Just to recap your memory, this is what that tan graph would have looked like. Okay, so we had a whole bunch of vertical asymptotes, as always would be the case. We have a whole bunch of x-intercepts as well, and it was over a restricted domain. Okay, so the primary purpose of this video is to actually look at equations involving the tan function. Okay, so in our first example, we've got the equation 4 tan x minus 4 equals 0. And we have to solve that equation for x, where x is in the domain from 0 to 2 pi, both inclusive. All right, so the first thing you need to do is take this equation and make tan x the subject. Okay, so what I mean by that is you want to get tan x by itself. And if you go through the algebra, you'll end up with tan x equals 1. The next step after that is to recognize what the reference angle is. And what I mean by reference angle, it's the angle from the exact value table that tan acts on to get a value of 1. Of course, that reference angle is pi on 4. So once you get the reference angle of pi on 4, you then draw a unit circle with the angle pi on 4 marked on it, okay? But before you do that, you probably should look at the quadrants in which tan is positive. So tan is positive in the first and the third quadrant. So let's get started in getting our solutions. So the first solution is in quadrant 1, as we said before, and the x value for that is simply pi on 4. Okay, nice and easy. It's exactly halfway between the x-axis and the y-axis. The next solution will be down here in quadrant 3. So how do you get to that solution there? Well, you start at 0, go anti-clockwise by pi, which is where this pi comes from. Then you go a further anti-clockwise by pi on 4, and that's why you add on pi on 4. Once that's done, we've pretty much taken care of our entire domain because there are no more solutions between here and 2 pi. Okay, so now the next step is simply to simplify whatever can be simplified. So you end up with x equals pi on 4 and x equals 5 pi on 4. So a nice, easy question to start us off. Right, so moving on to example 2, this one's a bit more complex. Let's see how it works out. So the equation is tan of 2x minus root 3 is equal to 0. And our domain is x from negative pi on 4 to pi on 4, both non-inclusive, union with pi on 4 to 3 pi on 4, also non-inclusive. So as we did before, you want to make tan 2x the subject. And once you do that, you end up with tan 2x equals root 3. Now, before we proceed to the reference angle, you need to have a look at this 2x over here. That's not just x, there's a 2 in front of it. Now, what that is a sign to, it's that the domain needs to be modified because this domain is the domain for x. However, the argument in our equation is 2x. So what you need to do is write out the domain first of all, and then modify it to make it look like 2x. So given our domain is just x, we're simply going to multiply everything in here by 2 to get it in terms of 2x. Okay, so you end up with 2x, element of negative pi on 2 to pi on 2, union with pi on 2 to 3 pi on 2. Now that we've modified our domain, let's go and find the reference angle, which is, of course, just pi over 3. Now that the reference angle has been found, let's look at a unit circle. So in a unit circle, we've got a positive root 3 here, so tan is positive, and a reference angle of pi on 3. So again, we've got quadrant 1 and quadrant 3. All right, so what's our first answer going to be? Well, it's just going to be pi on 3. And also you might notice there's a 2x on the left, not x, because in the initial stages of solving this equation, you need to actually get 2x, which is the argument of your tan equation. Now, you then get to the third quadrant by, just like we did before, you start at 0, go to pi, and then go forwards by pi on 3, and you end up with this. Okay, so by doing all this, you stop your domain looking at 3 pi on 2, which is just down here. So that's it. You don't have any more solutions in your domain. Now that you've done that, simply simplify both answers over there. And now that you've done that, simply divide both sides by 2. So x would equal pi on 6 and x would equal 2 pi on 3, which are the two answers for example 2. All right, so moving on to example 3, this is our second last example for this video. We've got an equation that looks a bit different from what we had before, in the sense that we've now got sine and cos in the one equation. You don't see any sign of a tan over there. However, if you divide both sides by cos 2 pi x, then sine divided by cos, as long as they have the same argument, of course, sine divided by cos, we should know, is equal to tan. So let's do that. Let's divide both sides by cos. So the root 3 remains on the left. Sine divided by cos is tan, and it maintains the same argument. And the right-hand side, well, dividing negative cos 2 pi x by cos 2 pi x would equal negative 1. So now that we've got that, let's get rid of the root 3. So dividing both sides by root 3, we end up with tan 2 pi x equals negative 1 and root 3. Okay, so that is the procedure for making tan the subject. Now that we've made tan the subject, let's go and look at our domain, because the argument is not x again, it's 2 pi x. So if x is between 0 and 1, both inclusive, then 2 pi x would be between 0 and 2 pi, both inclusive. So now that we've modified our domain, let's get the reference angle. So our reference angle is pi on 6, because tan of pi on 6 is 1 root 3. This negative will make an appearance in terms of the quadrants. Okay, so now let's draw a unit circle. And just a recollection, tan is negative in the second and fourth quadrants. So here's a unit circle with the angle lines in the second and fourth quadrants with pi on 6 as our reference angles. Okay, so let's commence our solution process. So we first of all have 2 pi x equals, and the very first solution you get when you start at 0, you'd go all the way anticlockwise to pi, and then you'd go backwards by pi on 6, and that's how you end up with pi minus pi on 6. Now we're going to go to quadrant 4, and how do you do that? Well, you start at 0, you swing all the way around a full revolution, and then you go backwards by pi on 6, which is 2 pi minus pi on 6. Okay, and that's it. That pretty much takes care of our entire domain. Now let's simplify these right-hand sides. So pi minus pi on 6 is 5 pi on 6, and 2 pi minus pi on 6 is 11 pi on 6. Now all we got to do is divide both sides by 2 pi. So the first thing that will happen is the pi's will disappear, and the second thing that will happen is these 6's will become 12. And that is why the answer to this question is x equals 5 pi on 12 and x equals 11 pi on 12. All right, let's now finally finish off with our example 4. Now this equation looks extremely complicated, okay, and we'll talk through a possible solution method for it. So here's the equation. It's tan squared theta plus 1 minus root 3 times tan theta minus root 3 is equal to 0. And then also we've got the domain of theta between 0 and 3 pi. So not only is the domain not a standard domain, we've also got an equation that's not a standard equation. So there's plenty of things going on over here. And also finally, we've got theta rather than x. So just a couple of things to watch out for. Right, so first things first is you might notice that this is a trinomial. Our first term is tan squared. Our second term is a coefficient with a tan, and our last term is a constant. So that is a trinomial right there. So a trinomial with a square, a linear, and a constant, at least in terms of the function tan theta. So that is actually what we call a disguised quadratic. And the usual technique for solving disguised quadratics is to let a equal tan theta. Okay, you can pretty much let a be any letter or any pronumeral. A is normally the one that we use. So we're basically performing a substitution. Once you then substitute a for tan theta, your equation becomes a squared plus 1 minus root 3 times a minus root 3 is equal to 0. Now that's a quadratic that is pretty tricky to factorize by hand. So we're going to enlist the help of our trusty CAS calculator to help us factorize this. Okay, so moving on to our CAS calculator, I'm in a brand new calculator screen. I'm going to go to menu, 3 for algebra and 2 for factor. Let's type in our left-hand side of the equation. So it's going to be a squared plus bracket 1 minus, and then control square root 3. Let's go right, close the bracket and times that by a, and then minus control square root 3, and that's it, okay? Now, given that we've got surds over here, we're definitely not going to be able to factorize over the integers. So if you just hit enter, it's not going to do anything because there is no factors of this over the integers. So you need to put comma a, which is basically the variable, and that tells the calculator that you want it to solve, rather factorize the equation over the entire real number field. Hit enter, and there we go. We get a really nice factorization of a plus 1 times a minus root 3. So popping back to our question, now that we've used our CAS, and there we go. We've got the factorization of that quadratic. Now that we've got the factorization, solving it is a pretty straightforward procedure using the null factor law. So from the a plus 1 equals 0, you of course get a equals -1, which of course leads to tan theta equals -1. Then from the other bracket, using the null factor law, you get a equals root 3, which of course means tan theta equals root 3. So what we've really got is a single equation of here, which is actually broken down into two separate individual equations. So let's solve these equations one at a time, keeping in mind our original domain. Right, so here we go. We've got tan theta equals -1, which is our first equation, and we've got our domain of 0 to 3 pi. So let's talk about our reference angle. Our reference angle is of course pi on 4 because tan theta equals -1, tan of pi on 4 would equal 1. So that's why our reference angle is pi on 4. Now let's draw a unit circle where tan is -1, and that is in the second and the fourth quadrants. So let's look at each of these quadrants one at a time. So our first solution is going to be in the second quadrant, which is pi minus pi on 4. Our second solution is going to be in the fourth quadrant, which is 2 pi minus pi on 4. Okay, so now just be wary of this domain of here. Once you go to 2 pi minus pi on 4, and then you keep going all the way till here, we've now just rotated by 2 pi. But remember, the domain goes all the way to 3 pi, which means we've got half a revolution left in the unit circle. And if you take another half revolution, you'll notice that you hit quadrant 2 again. And that is why we have a third solution at 3 pi minus pi on 4. Okay, but once that's done, you then get to 3 pi, and then your entire domain has been sorted out. All right, so we've just got theta over here, which means we only need to simplify each of these three expressions, right? So simplifying them, you get 3 pi and 4, 7 pi and 4, and 11 pi and 4. So that's the solution of the first equation over that domain. Now let's move on to the second equation. So our second equation was tan theta equals root 3, and it was over the same domain as previously. Okay, so what's our reference angle? Well, our reference angle is going to be pi over 3. Now let's look at the unit circle. So the unit circle is going to basically have quadrant 1 and quadrant 3 with a reference angle of pi on 3. Let's start looking at our solutions. So our first solution is going to be in quadrant 1 with an angle of pi on 3. Our next solution is going to be down here in quadrant 3. Okay, and then we're going to have one more solution because remember, we have another half turn, and that third solution is going to be back again in quadrant 1 with 2 pi plus pi on 3. Okay, so now simplifying these three things over here, we've got pi on 3, 4 pi on 3, and 7 pi on 3. Okay, so we've got a total of 6 solutions that have basically been derived from two separate equations. So it's where the show is not over yet. It's customary to basically put all these 6 solutions together and put them in ascending order. So let's do that. So here is our equation just as a recollection, and here are our solutions. So it starts at pi on 3, 3 pi on 4, 4 pi on 3, 7 pi on 4, 7 pi on 3, and finally 11 pi on 4. Okay, so I hope those examples there helped you to learn and understand how to solve tan equations. Thanks as always for tuning in, and see you next time.